In this video, we'll look at the non-homogeneous ODEs. A classical example is the forced damped oscillation. Imagine we have a system of a weight and a spring. Just these two things by themselves, it gives the free oscillation. If we add one dashpot, that's the damped oscillation. Now we apply an external force. This is the forced damped oscillation. The force can vary as a function of time. Say force is equal to F0 cos omega t. The general expression can be written down as my double prime plus cy prime plus ky equals to F0 cos omega t, where m is the mass, c is the frictional constant, k is the spring constant, t is time, and y is displacement. To write down the solution, there are two parts. The first part is the homogeneous part we call YH, and the second part is the particular part we call YP. Let's first focus on YP. YP can be written down as A cos omega t plus B sine omega t, and we can easily write down the YP prime and YP double prime. We then can substitute YP prime, and YP double prime to the original equation and solve A and B. A is equal to F0 multiplied by K minus m omega square over K minus omega square, then square, plus omega square C square. B is equal to F0 times omega C, then over K minus m omega square, then square plus omega square C square. We can also set square root k over m as the natural frequency of the system. Then k is equal to m omega square. We can write a and b as a function of omega and omega naught. Let's look at two cases. In the first case, we have the undamped forced oscillation. If the system is undamped, then c is equal to 0. Then you can get rid of c in the original expression to obtain a and b. A can be simplified to F0 over m omega naught square minus omega square. B is simply 0. Substitute a and b. You can obtain the particular solution for this oscillation. Yp is equal to F0 over m the omega naught square minus omega square, then cosine omega t. You can also write it as a function of k. Next, we can write down the general solution. The YH part can be written down as C cos omega naught t minus delta, then plus the particular part F0 over m omega naught square minus omega square, then cos omega t. From this solution, you can tell it is a superposition of two waves. To be more specific, the solution is a superposition of two harmonic oscillations. If you plot the particular part of the solution, it will look something like this. Let's have a closer look at the particular part of the solution. Let's just rewrite the expression. You notice there is a maximum value for that. This is when cosine omega t is equal to 1. Let's call this value A0. We can also write that down as a function of k. The part enclosed in this green shape has a special name called the resonance factor. From this expression, you know if omega is equal to omega naught, then A naught will go to infinity. This is when the resonance happens. What this tells you is if the frequency of the applied force matches the natural frequency of the system, then the system will just go crazy. You may have seen in some videos the bridge swings according to the wind, and if the swinging frequency matches the natural frequency of the bridge, then the bridge can easily break and the structure will just collapse. Let's move on to look at the damped forced oscillation. The particular part of the solution can also be written down as a cosine wave, where yp is equal to c asterisk cosine omega t minus eta. We will not do the derivation here and just write down the solution for c asterisk and eta. For c asterisk, it is equal to f naught over square root m square omega naught square minus omega square, then square plus omega square and c square. You can see the similarities and the differences from the undamped forced system. For eta, tan eta is equal to omega c over m multiplied by omega naught square minus omega square. To write down the entire solution, you will also plus the homogeneous part of the solution, which is the same as the undamped forced system. You now have had a taste of the damped forced system. In the next video, we'll apply what we have learned today to the electrical circuit to see how we can apply this to solve real engineering problems.